of some micro PMU data, and this happens to be in Alameda Power Standards Lab, and this is public data. So a lot of the data is protected, password protected. This one isn't. So what I just wanted to show you is how on the graph on my laptop here, I can zoom in and zoom out. So I can see, for example, that earlier in March, there was some big disturbance event. And right now, when I'm zooming, it shows you the minimum, maximum, and mean for each time interval. And then it's downloading the data. So I'm online here through your Wi-Fi, talking to the server back in Berkeley. And I just want to show you how the zooming, goes. I'm going to hours, and at this rate, okay, there was apparently some disconnection. Yeah, I don't know exactly what happened here, but what I wanted to show you is just the speed of going to individual data points and then zooming back out, which is pretty exciting. And I think basically a voltage was disconnected there. There's a whole lot of fun to have with this, but I'm going to let Thomas talk about the hardware. And we'll give you the URL, and you can actually see archive.upmu.org. So you can go to that, and you will actually be able to retrieve this data.
All right. Well, thanks, Sasha, for the warm welcome. Okay, so for those of you who have taken the liberty of checking my LinkedIn, you'll notice that my title says retired engineer from Power Standards Lab, and you can see it right there. So I've actually left the company, and don't get me wrong, I've had a great experience working with Power Standards Lab for the past 10 years. But eventually my desire to live in Asia overcame my desire to continue working. So here I am. Sasha was nice enough to invite me over. She said, hey Thomas, I'm coming over to your neck of the woods. Why don't you come out? And I told her, well, you see, I'm actually traveling with my best friend Charles right there. So if you would be willing to accommodate him as well, I'd be happy to come. So thank you, Sasha, for inviting us. So before I begin, I wanted to talk a little bit about our company. So we are Power Standards Lab. We initially started as a testing company for the semiconductor industry, and we eventually pivoted to product design and manufacturing. And the problem with our name, Power Standards Lab, was everyone is really confused. Why is a company that's named Power Standards Lab selling products to us? So we decided to rebrand our company as Power Sensors Limited, which is a division of our parent company, Power Standards Lab. But from top to bottom, we're still operating in the same fashion as we've done in the past. Okay? So we design and manufacture the PCube3, which is a high-end power quality analyzer. It's a triggered waveform recorder, long-term data logger, and it does all these automatic recording features and communications. And our engineers actively participate in writing and maintaining international standards about how you measure electric power. Our CEO, Alex McClecker, is the chairman of quite a number of the IEC committees that writes standards on power quality measurement methods and harmonics measurements. Okay, and over here you see all the guys from our team. We've got the firmware guys, Chow and Arya. Now Arya is our DSP guy, and he's also one of the most instrumental guys when it comes to developing the micro PMU. So I'm happy to say that I've worked with a tremendous group of people throughout my career, and I wanted to give them a little bit of visibility here. So, all right, let's move on. Okay, so the PCube3, we've taken a lot of trouble to make the PCube as accurate and precise as possible, because that's the requirement from all of our customers. Now, if you look over here, you see our specified accuracy is plus minus 0.05%. But in reality, when we calibrate all of our PCubes, our factory limit is half of that. And typically, when we calibrate a PCube, it's actually 0.01% of our reference. And by doing this, by publishing our spec at least twice of our factory pass-fail threshold, we can guarantee that you will not need to calibrate your high-end, accurate, precise instruments until 10 or 20 years. And we got this data after analyzing our direct specifications of all of our internal components. And so you can see for voltage and current, we have the same accuracy specs. Now for current, like Sasha was mentioning earlier, we are at the whim of whatever external CTs you guys decide to use. We also sell external CTs, which are extremely accurate as well. And in case you don't believe me, if you buy a PQ or micro PMU, anything with a serial number, you can go to our website, enter the serial number, and you can retrieve our calibration certificate. And we have, I think, literally hundreds of tests that we run the PQ through before we declare it passed and ready for shipping. So in this, you'll see all of our reference equipment, you'll see the last calibration date, and all of our reference equipment is certified to the master volt and master amp and ohm of the United States. And we call this NIST traceability. So our reference equipment is one step removed from the United States reference. All right, so going into the PMUs, so if anyone's interested in learning how you measure synchrophasor measurements and how you communicate to the database, you can look at this IEEE standard. Sorry, how do you go backwards? Oh. You can never go back? Right. Oh, here. Let me use the keyboard. This one, all right? Okay, there we go. Okay, so before we developed the micro PMU, we had to examine the specifications of the existing PMU technologies on the market. And what we found was all of the PMUs were roughly 1% TVE, plus minus 1 degree, which is perfectly fine for transmission, where I thought the phase angle differences were 5, 10, 15 degrees, but as Sasha's map points out, we actually see phase angle shifts of plus minus 50 degrees on the transmission. So I learned something new today. But basically, for that type of application, these specifications are more than enough. But now we're talking about distribution, it's a whole different ballgame. Now, in all fairness, I've seen recent PMUs with better specs than this. For example, instead of 15 readings per second, I've seen some newer models with 60 readings per second. But the TVE is still not up to par for what you need for distribution. And the typical PMU installation requires a network of PMUs constantly streaming data to the database, which they call a PDC, or Phasor Data Concentrator. Now what happens if you drop a packet? Well, you've just lost that data. It's gone forever. So we've identified a weakness in how the traditional PMU technology is communicating the data. So based on this information, we've decided plan on how to develop a micro PMU. Okay, so for a distribution-capable PMU, it needs to be precise enough because the cable runs are orders of magnitude shorter than what you'll find on transmission. So we're going from 5, 10, 15, 50 degrees to literally millidegrees. A millidegree is, I think it's half a microsecond. So we really need that tight precision. The recording rate, on the distribution, you're going to see changes that occur much faster. So we want to increase our recording rate from 15 or 30 or 60 readings per second. We record at twice the mains frequency. So for 50 hertz systems, we will record at 100 readings per second, and for 60 hertz, 120 readings per second. And for transmission, what you'll often see is all the cables are running overhead. But on distribution, the cables go overhead through substations with many different transformers. They go underground and back up again. So we have to be able to adapt and be flexible enough to accommodate all of these environments. And of course, you will most likely be using cellular modems because you don't have the IT infrastructure out in the poles. And what we've observed with cellular modems is you'll get frequent communications outages, even with the best network provider in your country. We use Verizon in America, which is considered the best carrier as far as signal integrity, but we still observe communications outages, once or twice a month. Yeah. And of course, there's a lot more measurement points in distribution. So, moral of the story is, if you want to do synchrophasor measurements on distribution, it's got to be cheaper and better. Now, I'm an American, so I've been conditioned to believe that the free market will always find a solution given a problem. And for the most part, I do believe that's true. I'm ashamed to admit it. But in this case, I actually see the other point of view, which is no company that's dedicated to making profit will actually make this on their own accord. So fortunately, the US government, the Department of Energy, was kind enough to help us develop this amazing product. So the DOE, the ARPA-E branch of DOE invested, I don't know how much, but it was certainly enough for us to finish the development of the product. There are the traditional PMU specifications, again, and then if you look over there, those are the specifications that we're able to achieve with the micro PMU. So as you can see, everything is about, orders of magnitude better than existing PMU technology. So I wanted to talk a little bit about the total vector error. So that red circle you see is a 1% boundary. This is a signal. This is one of many tests that we did to validate our design. So the red circle is the acceptable limit for a signal that is 120 volts in America. So in the real and imaginary plane, it'll go out to 1.2 volts. We have 4 micro PMUs, all measuring against, we have 3 PMUs measuring against one, which we considered the reference. And we did 9,000 measurements on all of the PMUs, and they all fell to within 0.05% TDE. Now I want to stress the difference between accuracy and precision. For all we know, now the true reference value is not in here. So basically what this is telling you is the precision of our micro PMU. For all we know, the actual value could be out in the upper quadrant or lower quadrant. But basically this is just to illustrate how precise our instrument is. So with 9,000 measurements per PMU, we're all getting within about 0.05%. So a little bit about the micro PMU. It's basically a power monitor. You have 3-phase inputs on the back. Now the synchrophasors do all their measurements line to earth. This is important because you will eventually develop a potential difference between your neutral and earth. So all of our synchrophasor measurements have to be done line to earth. And then you will see 8 current channels here, which is how we designed the original PQ3. But when we turned it into a micro PMU, we're only using the first 3 channels. Now, for synchrophasor measurements, fortunately, it's the voltage measurements that's critical. The current measurements are good to have, and they provide some context as to what's happening with all phase angle shifts, but it's the voltage measurements that you have to do. And then, of course, shouldn't forget this. This is the GPS receiver. So this is an integrated receiver and antenna, and we did that specifically to limit the distance between the 2 modules. And by doing that, we can actually compensate for the delay introduced by the length of the GPS cable. Now, the speed of light is roughly 300 million meters per second, which is a very fast speed, but if you have a cable run that's 300 or 500 meters, we've actually observed noticeable delays due to the increased cable length. So. We support PT and CT ratios up to 50,000 to 1. So this means if you want to use it for transmission, you can, and we have certainly done so in the past. And each PMU comes with 16 gigabytes of onboard storage, which is good for about 2 to 3 weeks of data. And if the storage gets full, we simply start overwriting the old data. So you don't have to babysit your instrument, you don't have to make service calls to the field, it'll just keep going. But once it's connected to the Better DB instrument, it'll just automatically push the data out. Okay, so we have 3 voltage, 3 current. We report magnitude and angle for each channel. We also compute all of the distillates. Basically, these are additional parameters that can be made using the data from one PMU. So we can derive the frequency from the raw phase angle information. There are 2 definitions for frequency in this case. There is the IEEE C37 definition, and then there's another definition that we use, which is simply the first derivative of your phase angle. And then we also compute your real power, apparent power, reactive power, and displacement power factor. Okay? And for anything else that requires 2 PMUs, for example, phase angle difference, that would have to be done on the database server. Okay? So as I mentioned earlier, once the PMUs are connected to the network and properly configured, it automatically pushes the data out. You don't have to worry about opening firewalls or anything like that. And we still support the IEEE C37 communications protocol. So we have a lot of companies that are already pulling the data from our PMUs to import the data to their PDCs. And of course, we can compensate for the phase delay due to the cable length.
How often do you send it?
Oh, so from the PMU, by default, I think it's 2-minute chunks. You can set it as low as 1 minute. And in our testing, we're able to send out the data about once per second, but that's still undergoing more testing because with 1 second, it introduces different issues with the writing rate to the hard drive. So, but we've observed very good results with what we've done so far. So with 1 or 2 minute chunks of data, we've achieved nearly 100% coverage. So in our context, the word coverage means how much data do you have that covers the entire recording period. So, 120 measurements per second times 12 channels, we've achieved almost 100%. Where did I put my remote? Sorry. Okay, so I wanted to talk about some of the lessons I've learned as acting project manager for our initial investigation. So whenever we have a data outage, everyone starts panicking. Why is the data gone? Is power off? Did somebody forget to pay the bill? No. Is there enough cellular reception? Did we lose GPS? Maybe someone installed a roof cover over the antenna. Did somebody schedule a site shutdown without telling us? So there's all these important questions that need to be answered. So it's really important that you install the PMU in a... I think my battery's dead. Oh. Let me go backwards a little bit. Okay, cool. Okay, so just go forward a slide. It's not going?
I think it's your laptop.
No way.
It's
a very high-end machine. There's no way it's working. All right, give me 1 second. Okay, let's see. Microsoft Office? Yeah. Okay.
yeah, it's hanging.
It's hanging. Okay. Okay, let me just close and reopen my presentation. For those of you that are wondering what this picture is, it was taken from the Sky Bar in the Siloam district in Bangkok. I was going to take this back, but we ended up going to a different one. Long story. All right. It works now? Okay, so before I get to that last part, here is a sample of what the PMU data actually looks like. So I grabbed some of the data out of a PMU that I've worked with recently. Well, recently, meaning 2016. So basically what you'll see here is every row represents 1/120th of a second. You'll see your date and time. The log state indicates the health of your PMU. If it's a non-zero value, or 32 in our case because we implemented some new parameters. But basically 0 or 32 indicates that everything's operating okay. If you have a 2, 4, or 8, it indicates that you've lost GPS or there's some other issue going on that's making your measurements unreliable. But you can either look at the data automatic or manually like this, or you can just import it into your BetterDB database and look at the data there. All right, so, yeah, this is where I wanted to go. Okay, so, based on my experiences as a project manager, working with many different utilities, I've noticed that each utility has their own requirements. We had one utility that wanted all of the PMUs mounted on the pole. We had another one that wanted a portable box that they could just drop at the tab mount. And then we had another one that wanted to mount it in the wall. We had another one that wanted to mount it in the panel in the switchgear. And of course, as the equipment supplier, we were obliged to accommodate all of these requests. And I'm glad to say we did eventually accommodate everyone. But it was real struggle to do it. So basically, if you guys can, if utility guys can have their own installation protocols and take care of it themselves, I've noticed that those are the projects that go a lot more smoothly as opposed to the other utilities that have all sorts of requests. Those take a lot longer to fulfill. So something to keep in mind. And of course, a lot of the utilities will already have the voltage and current transducers. We need to make sure that the input impedances match our PMU. The voltage inputs are about 5 mega ohm input impedance. The current inputs are about 33K, and that's by design to work with our current transformers. Now, we observed some issues where our current channels were being clamped down to 0 because the input impedance did not match the transducer. But we were able to come up with a solution eventually through firmware. Networking costs. So each micro PMU generates 16 gigabytes of data per month. So if you can imagine you had a fleet of 100 PMUs, you're getting 100 times 16 gigabytes of data per month. So that's very important if you're going to use cellular modems. Just to give you an idea, our data plan was, we got a group deal with all of our modems, but we were talking maybe hundreds of dollars per month per PMU just to get the data out. Yeah. So now, I don't know how much your cell phone bills cost in the Philippines. I know that a lot of telecom companies have a lot of monopolistic power in the States, but hopefully you guys probably have better pricing than we do. But to the extent that you can, if you can use your local area network, that's good, but there's also other challenges. If you ask your IT department to open a port to your network, they're going to say, no way, get out of here. If you ask them to give you VPN access, that might be a possibility. Okay, but pros and cons to each one. Okay, so troubleshooting a data outage. This is one of the biggest problems I had to deal with as PM for this project. So I've literally seen all of these issues at one point be the root cause of the data outage. Now, so given that, you want to make sure that you install your PMU at a very accessible site, because we installed our first few PMUs in a gated area, and every time we had to go check on the PMUs, it resulted in a very expensive service call. So now I don't know how much the service calls cost out here, but back in the States, the service calls can get very pricey, and so you want to make sure that you have good, reliable access. So please choose your sites very carefully. So I wanted to talk about some real-world measurements that we've done in the past, and some of this might overlap with what Sasha's talked about already. But basically, right here we have 3 PMUs, one at Grizzly Peak, which serves Lawrence Berkeley National Labs. We have one at the PSL main office in Alameda, and one at UC Berkeley. Now, these 3 locations are separated electrically by 40 kilometers and 3 substations in between. If you look right there, you can see the voltage dip occurred on all 3 units. So we know that the voltage originated on the transmission level. And if you zoom in, you can see just how well aligned the voltage dips are. Over here we have a voltage dip that was recorded at Grizzly Peak, and that was obviously caused by this large load kicking in at the same location. And this is about a 2% voltage dip. This is pretty common, you'll see this all the time. But what you won't see is that we could also pick up the voltage at our main office at the exact same time. Instead of a 2% dip, we were able to pick a 0.03% sag at exactly the same time. So this load that kicks in 40 kilometers away, in between 3 substations, we were able to pick it up using our micro PMU. So that just shows you how precise our measurements are. Okay. And last but not least, here is a classical synchrophaser measurement at Lawrence Berkeley. So we have an underground cable that's about 600 meters, and basically the current went up, and we were able to observe a 8 millidegree shift in the phase angle due to this. Now, you could not measure this with a traditional PMU. So this was kind of our validation that, yes, the micro PMU is capable enough to be used in distribution. So, yes?
How were you able to achieve the kind of precision that you got from
how were we able to achieve the precision? And so, as I showed you earlier, it all comes down to our reference equipment. So we invested a lot of money into good reference equipment, which we use to calibrate all of our P cubes. And we by design, we set very tight thresholds during calibration, and we use very tight tolerance parts in our bill of materials to achieve that precision. Any other questions? All right. Yeah.
How does the accuracy affected by the temperature in the...
Yeah. So our written spec is designed to cover that range from plus and minus. So let me go back to our written specification. And it's frozen again. But basically, our written specification is what 0.05% percent of reading and percent full scale, which is how you're supposed to specify your accuracy for voltage and current. So basically, our PQ meets revenue. There are two standards that define requirements for revenue grade measurements. It's called ANSI class 0.2 and IEC class 0.2S. And to be able to meet these accuracy requirements, you have to meet all of the accuracy requirements at many different operating conditions. So you have to make sure that it's within accuracy at the low range of your temperature spec and the high range of your temperature spec. And also again for humidity and vibration. There's a lot of environmental tests that we have to do to conform to ANSI and IEC class 0.2 in order for the PQ3 to be considered a revenue grade meter. So the fact that the PQ3 is a revenue grade meter just makes it a lot easier for us to convert it to a PMU. Okay, well if nobody has any questions, I think we can wrap this up.
So according to our schedule, thank you Thomas for the presentation. Thanks Sasha. According to our schedule, it's 11:25 right now. We're open for some more discussions with you. So we heard about the overview from Mike earlier, and of course the first set of presentation. If you have any questions on any of this, we welcome those. It's either from the overview of this project and why we're here. Actually, if you want to ask some more, why we're here, or specifically for the first set of presentations from Sasha and Thomas. Any questions?
What's the range of the cost?
Yes, sir.
Cost of the unit.
Cost of the unit.
The range.
Range. I would like to answer that, but we're still negotiating right now. ESL, the Power Standards Lab, have their own quotation, but we don't know the cost, landed cost here in the Philippines yet. So we're still, that's still in the negotiation stage.
We have a distributor here in the Philippines that is taking care of the import duties and shipping. So we're still negotiating the final costs to the university and the utilities.
Even the ESL cost.
So the ballpark price.
It's in the few $1,000s US. Now I don't know what the exact price will be in the Philippines, but it's ballpark with the PMU and all the necessary modules, power supply, the synchrophaser, and the GPS. It's going to be a few $1,000s. I'm not inside sales, so I'm not in a position to give you an exact figure. I'm going to get myself in trouble if I give you an exact number.
With regards to the database, it's going to be a big challenge for utility to invest on large amount of storage when it comes to using this PMU. So is the database compressing the data so that not too much storage is required?
Yes.
Oh, yes. I deal with the instrumentation side, so.
So I can say a little bit more about the database, which is that we have explored a couple of different ways to actually store the data. And one approach is on, what they call bare metal, to actually have a physical server, which I think traditionally for many utility companies feels safer than to have data communicated by way of the cloud. Although our computer experts tell me that really there isn't a difference. So the bare metal server brings with it the responsibility of having IT personnel dealing with, the server hardware. And the data does accumulate pretty quickly, although storage is not as expensive as it used to be. So, our colleagues in computer science, now when you talk about tens of terabytes, they just don't even bat an eye. I mean, that's just normal, kind of everyday stuff for them. So the cost of having the accumulated data storage is really, I would almost say, negligible. What's expensive is to have the capability of the fast data ingress into the system and the ability to take it back out. So it's getting to it fast, putting the data in and out fast. That's the performance requirement for the server. And that process is greatly sped up and facilitated by the design of the database. And I can give you references about it. I can't really speak in detail about it, but there is a lot of compression going on. And according to Michael Anderson, basically the whole thing is 2 orders of magnitude faster than the next fastest commercial database, which at the time he made the comparison was Cassandra. But so, building your own server and running the software is one approach. The other approach is to simply outsource that and send the data to be handled by a server in the cloud. Now, you can contract with Amazon, for example, or some company for cloud services. That means you don't have to have somebody who actually deals with the hardware. And there is a company called Ping Things in the US with whom we're working to basically take the data hosting services and some of the analytics to make that available to utilities as well. And that's a global thing because these days, you put stuff on the internet. Many utilities in the US that we talk to have a little bit of a queasy feeling about data being in the cloud, but in fact, the layers of security that are applied are really as good for data in the cloud as they are for data. If it has to travel at all from one location to another, if it goes to the cloud, it's just as safe as anything else. I mean, unless you had a physically, completely isolated system, which you're not going to have when something is in the field. But what's also, I think, important is that it is a network that's really separate from other data that utilities have right now, and I think the data security issues are going to be interesting when you talk about integrating, for example, micro-PMU and SCADA data. And so I think there's still going to be work to be done about guaranteeing the security of everything when you start going into systems that could, for example, deal with actual real-time control of utility systems. But so that's a long way of saying there's really several different options. The volume of the data is the least of the concerns. And I think the way of the future is to do cloud hosting because then, again, the terabytes that you accumulate are no big deal. And you're gathering more data over the course of months and years. You don't have to pay for all the storage up front. You pay as you go. So that makes a lot of sense. But then research projects are a little bit different from commercial deployments. And so there's also sort of the issue of how do you design a good pilot or a research project that might be at a smaller scale than something that ultimately is going to scale up to hundreds of sensors. There's a long answer. I hope I addressed your main point.
Another question. Do you think there's a possibility of opening this technology with other line equipment manufacturers like, for example, a recloser controller? Because right now, if we are going to install this sensor alone, it's going to require a PT and a CT in the distribution line, and then this high precision measurement. So if you combine that with perhaps a line recloser, then you save up on so many installation costs like the PT, the CT, and also the functionality, of course.
That's exactly right. So what we have done in our project so far is we have specifically gone to locations where they already had PTs and CTs installed. So reclosers are a great example. Sometimes capacitor banks also would have PTs and CTs there. And so rather than going with this, optimal placement algorithm, we say, well, our optimal placement is wherever we can put them inexpensively, and then we'll just we'll start from there and see. So I think that's a really viable approach. But the next step, as I think you say, is wouldn't it make sense to embed the sensor inside the other hardware? And I think that is a really logical future development. And one place where this discussion has come up back in the United States is in the context of solar inverters. Because inverters already have a whole bunch of power electronics in them, and to put a synchrophasor in there as well could make a lot of sense for a lot of reasons. So I think where we are in the technology to market path, right now we're focusing on the analytics with the PMUs by themselves, and then I think it will be up to the private sector to sort of take those pieces that we've developed and say it makes economic sense and we can market it if we integrate it with this, or this piece of equipment. But I think you're exactly thinking along the right lines.
How is this different from 61859-2 sample value standards?
I'm not actually, I don't remember exactly what the 61850 in detail requires. I think it is a faster, it is a higher data rate.
I think this one is faster because it sends 120 messages per second. Right. I think the LE only sends 80 messages per second.
And then there's a C77118, which is also slower. That's, I think that ultimately it won't matter so much as long as we can integrate with different standards that are in practice. And the hardware itself is certainly capable. In fact, we have in some settings used the C37 protocol, which basically it compromises the quality of the data a little bit. And there are trade-offs, because it's also how fast do you want the data, how fast do you want to do the computation, and then how frequently you report it. I think the short answer is that the Berkeley Tree database approach has been really good for the research environment, and depending on how much analytics versus how much control will be done in the field, it might be more practical to interface with a different standard, and there's no reason that can't happen.
You've alluded to this in your presentation, but I'm not quite clear how it's really going on. But are there any collaborative overlaps or interfaces with smart microgrid controller research?
So microgrid controller research, there is one project in the US that we have worked with, and that was in the Philadelphia Navy Yard. It was a project, or it is a project, but our part of it is now finished, sponsored also by the US Department of Energy, and the commercial vendor is Alstom GE. They are basically studying the question of how does the micro PMU data, how could it inform their microgrid controller. There are two other US vendors of distribution control systems that are exploring, with whom we're collaborating on a follow-on RPE project, that to basically answer the same question, how can the micro PMU improve their controller operation? That's not microgrid specifically, but it is for either solar PV or for storage resources. One example that I think has a lot of promise, actually, particularly in the area of resilience, is storage resources, and it could be flywheels or it could be batteries, but at the scale of a substation or a distribution feeder. And so we're working with these two vendors. One is called Smarter Grid Solutions, the other is called Doosan Grid Tech, which is a Korean company that recently bought a small firm in Seattle, Washington, that used to be called One Energy Systems, and they make a battery controller. And they actually came up with what's called a MESA standard for controlling storage resources. So we are working with them to basically see how can they usefully integrate the synchrophaser data to improve their control algorithms. And one thing also that I have to say is, while I love Power Standards Lab, and we have and Thomas is great, and Alex McEachern is a good personal friend, which is why we came up with this research in the first place. When Alex and I had lunch one day and said, "Hey, how about distribution synchrophasors? What a cool idea! Let's try it." But I think the reality is, Power Standards Lab won't be the only vendor in the field doing hardware that can do distribution synchrophaser measurements. They've been the first to put out a device like this. I think there are going to be other manufacturers, other really market niches, for equipment that's good at doing different things, that's going to be the right choice in different places. And PSL may expand their product line, or other vendors who are now big in transmission synchrophasors may, go into the distribution world. And I think, we'll have to keep our eyes open. Everyone will have something to contribute.
For what it's worth,
Again, going back to my justification of, being conditioned to believe that the free market will find a solution, this is exactly what I'm talking about. I think if there are more companies that eventually do make a distribution level PMU, that will ultimately result in more choices and lower prices for all the buyers. This is something that I think will eventually happen. But this is still kind of a new technology, so I think it's still going to take a little bit more time.
So I think the way I would like to wrap that point up is that as the research community, and by research I don't just mean academics, but I mean industry people who really have the field experience and the knowledge of the esoteric knowledge of how does stuff actually work. Industry working in collaboration with academia, we really, need to define the needs and the opportunities for the private sector then to step in and provide us the tools that we need. But, like I said, it's a very large terrain of discovery, and it's going to take everybody working together. And right now you're probably wondering when's lunch, right?
At the moment it's just PSL that's doing the equipment, nobody else is.
So at the moment, it's only PSL, far and away the most precise and high performance device. There are a couple of competitors whom I could mention. So one is Schweitzer Engineering Lab. They are the standard provider of transmission synchrophasors, and they have also pursued the strategy of embedding synchrophasors in relays specifically. And I heard some staggering number of Schweitzer PMUs that are actually installed in the United States without being activated, or without the owners necessarily being aware that they have these PMUs, because Schweitzer decided, we'll just put the PMU in there, and then someday we can flip the switch or update the firmware, and the relay, the digital relay will turn into a PMU. I don't think the U.S. is unique in that. I think in Mexico, I've learned, there's a lot of PMUs that aren't recording data yet. And China is supposed to have PMUs at every single substation, and I don't know if they're gathering all these data. But so, and I don't know which Chinese company would be a major manufacturer, but in the US it's Schweitzer is the big leader. There's another group, but so, having said that, they make great synchrophasors that are designed for measuring transmission phenomena. They're not designed for distribution phenomena. So basically, the vector error that they will come up with isn't going to tell you what you need to know for the distribution level analysis. So it's a great product for a totally different purpose. There are also colleagues at the University of Tennessee, where I showed you the graph earlier. They have a gadget they call the distribution, the FDR, the frequency disturbance recorder, which they chose that word carefully because it's kind of a PMU, but it's not a very precise PMU. It's really designed to measure the frequency and not the absolute phase angle relative to other locations. So they will give you phase angle measurements, but they're not extremely precise, nor do they need to be for their purposes, because they're looking at, again, wide area phenomena. And they're able, to their credit, to manufacture that FDR unit and sell it, I think it's like on the order of a couple $100 instead of a couple thousand. So it's an order of magnitude cheaper, but it's more than an order of magnitude less precision and accuracy. And so, which is, you know, not to say it's an inferior product, it's actually a really great product for doing a certain job, right? So those are the competitors that come to mind. National Instruments is another company in the US that makes PMUs and doesn't make PMUs of the micro PMU kind. And I'm trying to use the term micro PMU actually as a generic term, sort of a high precision distribution centric PMU. And right now PSL is still the only company that makes anything like it.
Just to clarify, at the distribution level, it's PSL only, not Schweitzer or the Mexican or the Chinese.
So I'm going to, mostly the answer is yes, at the distribution level it's PSL only. There is one exception. So Schweitzer PMU relays are installed at distribution substations, so people might tell you they are distribution PMUs, but to be a distribution PMU, really you need to make a comparative measurement somewhere down on the circuit. And I'm not aware of all but more than one instance where people are using Schweitzer PMUs to do that. And this one use case is actually an interesting one and not one I talked about. San Diego Gas and Electric in Southern California, and some colleagues at UC San Diego have been working on an approach that I think they've demonstrated now, measuring a phase angle separation along a distribution circuit for the purpose of detecting when there's a physical break in the conductor. So to do that, and what they do with that information is they have a very short latency, which they can do because the measurement doesn't have to be very precise. You can detect whether a connection is open or closed by seeing that the phase angle difference across it suddenly stepped up. You don't need a very good PMU to do that. You know, you need to see the angle to within a few degrees. I mean, because as soon as you disconnect, if you physically break a conductor, I mean, that phase angle is just going to fly apart. So you can use the worst possible precision of PMU and you'll still see that. What you need is a very, very short latency, because what SDG&E is doing is they are sending that signal to their protective systems, and they are disconnecting, de-energizing a conductor before it hits the ground. So they have basically a second or a second and a half time between when a distribution conductor breaks apart and falls down and hits the ground. So they're able to use the distribution synchrophasor data to de-energize that line before it hits the ground. So that's a distribution application that they're doing with PMUs, not PSL. It happens to be an application that doesn't require a very good synchrophasor measurement. It just basically detects, well, is it connected or open? So that's the one exception that I'm aware of.
Also, I'd like to make a comment on that.
So there's PMUs that are used on distribution circuits, and then there are PMUs which have enough precision to do comparative measurements on a distribution circuit. So I don't think there's a standard term for that. We want to call it micro PMU, and you've probably seen it written in a few different forms: UPMU, mu PMU, which is a prefix for micro. And I got some pretty valuable feedback from some of our friends in China and Japan. Is I think we should harmonize it and just call it the word micro PMU, because the Greek letters and the letter U may not be immediately apparent to people in other countries.
Non-scientific.
Exactly. So.
And yeah, so you reminded me to add one more comment, which is that in some cases people have PMUs connected at the primary or secondary distribution level. So they might even have PMUs, whether it's Schweitzer or the University of Tennessee, plugged into their wall outlet at 120 some volts or something. But what they're looking at, the way they are studying the signal, is they're looking at their measurement in reference or comparison to some location that's hundreds of kilometers away. So they're really looking at the transmission system from a distribution location. And one example, a great example of that, is a colleague, Professor Mac Grady at Baylor University in Texas. And I wish I had a graph. American politics is fascinating, and American geography is fascinating, and the state of Texas is very fascinating because electrically, there are three synchronous AC grids. There's the eastern United States, the western United States, and Texas. So Texas is known for its independence and doing their own thing. So they have their own grid there, and they're also, and this is a wonderful playing against stereotypes. See, in California, we think that people in Texas are sort of, very conservative, and they like their cowboy hats and their guns and all. Well, it turns out that the people in Texas actually really like their wind power. And Texas, some years ago, far surpassed California in their installation of wind power. So they're actually much greener in that sense than we are. But so Texas is an interesting thing because they have, a large, I don't know how many square kilometers, but very high penetration of wind generation, in the tens of percent. And so when you're looking at the phasors across the state of Texas, it's basically an indication of what the wind speed is doing in West Texas. And they're going to probably have some stability issues with that. We don't know yet. They haven't had big outages yet at Texas. A colleague of mine who used to run the California ISO thinks that they're going to have big problems. But so Texas is a place to watch for, basically, if you're a power systems fanatic and you love to, just for the science of it, look at what an unstable grid might look like. Texas would be an interesting case, and to see how much variability and how low an inertia they can get away with as they are, adding more and more wind power, which I think is a great thing to do, by the way. But so our colleague Mac Grady has 3 places where he has plugged in synchrophasors on the secondary side, again measuring up through several layers of loaded service transformers, so the measurement can't be very accurate, but you don't need it to be accurate if what you're looking at is the stability and the phase angle separation swings of tens of degrees depending on wind speed across Texas. So that's another example of sort of distribution-connected PMUs that are really doing the job of transmission PMUs. And, there's this whole little adventurous sense of making rogue measurements there because in the United States, there's a whole different layer of, again, security and protection of synchrophasor data, academic researchers to get transmission synchrophasor data. And sometimes it's easier just to plug something in yourself to measure it. And, that I think is going to be an interesting evolution over time because the more equipment is going to be around that you can basically plug into your service voltage at any outlet, the less claim to privacy or secrecy of any kind we're going to have on the grid, because the grid is going to become more transparent. I can already plug a micro PMU in at my house and learn something about my neighbors. Do I care? Not really, but I think ultimately that's going to be, you know, another ongoing discussion and an area of research. They're nodding like it's lunchtime.
One more.
Just a high-level question. So the initial effort in research was triggered by ARPA-E funding. I guess I assume that was named with reference to DARPA from a long time ago. And if I have my history approximately correct, DARPA led to the internet. So what is the thinking of ARPA-E in terms of IP, the fruits of all this research? Is it going to be something like funded by U.S. taxpayer but released to the world?
Yeah, so a good point. So ARPA-E as an agency was modeled on DARPA, the Defense Advanced Research Projects Agency, but is organizationally separate, so it's not defense focused. And I forget what year it was created. And then -E is for energy specific project. So their mission is to basically bridge this transition from original technology research ideas to bringing technology to market. So it is a very, let's say, surgical subsidy. And they put a lot of effort and attention into basically working with research teams to think about the transition and handing it off to private companies so they can go run with an idea. So they fund ideas, and I don't know the total budget, and I also don't know how much their total budget is going to be cut, because there have been conversations in different ways in recent months about they're going to eliminate ARPA-E, or no, they're actually going to appropriate more funds to ARPA-E. And it's very crazy times in Washington, D.C. We don't know exactly, or I don't know what's going to happen with ARPA-E. But they have been very successful at basically nurturing far-out crazy technology ideas that were just too risky for the private sector to entirely develop on their own. And then some percentage of them never go anywhere, and it was worth a try, and then some percentage get over the cusp into commercialization, and we hope that that's where we are. Certainly the micro PMU as a hardware device is over that cusp. It's commercial, it's ready, one can buy it. What we also hope to do, and ARPA-E has been very specific about that, is we need to develop the applications for these data into commercial packages and things that are out there for utilities to buy, but also to build on and develop further. So there's actually, so you asked about the IP, so Power Standards Lab has all the patents on the hardware. The work that the University of California has done on algorithm development and so forth, that's all in the public domain. So we try and publish as much as we can. There's code on GitHub, and really what we care about is that other smart people in the world take it and run with it and do cool things with it. Because, you know, the reason we're in this is because we care about having clean, reliable electricity, and the more people collaborate, the better. So they're going to, we have, as I mentioned, follow-on projects with some private companies, and in each case they can produce their own intellectual property, and they can patent some of the things that they do, building on our open source code and some of our research ideas and outcomes. They can package it and put their secret sauce in it and tie a ribbon around it and sell it as their product. and have some exclusivity of their product, but the basic research on the fundamental algorithms and everything that we do at the university is open.
Also very high level. What's your take on the term smart grid? And everybody's saying, using the term smart grid, it's not kind of a marketing term. But what's your take on the whole issue of smart grid, and how does it fit into smart grid? If you were to draw smart grid, is kind of a very fuzzy term, but if you do a Venn diagram of smart grid, is the microsynchrophasors part of that? And what part of smart grid is not micro-PMU?
So, I wish I had another hour to talk about that. So the part that we don't deal with directly, I think, is the market aspect. Like, a lot of people, when they talk about smart grids, they're also talking about transactive energy. They're talking about intricate processes of buying and selling different services or behaviors on the grid. So we're not touching that side of it, and for that, micro-PMUs and analytics are enabling, but, well, I say we're not touching that in Project 2, but in Project 1, we are, that project is very much touching the transactive buying and selling parts of it. So in this case, the physical instrumentation is enabling transactions that otherwise you couldn't verify or validate or compute what would be the right way of doing it. There's one diagram that I would show, to illustrate what's a smart grid, and I had it, but not in my show. It's basically looking at, again, logarithmic time scale of all the different kinds of control decisions that you would make in the grid. And they range from, microseconds to decades. It's actually about, if you think about it, 15 orders of magnitude of, different time scales on which, let's say, an inverter switches or protection system actuates. And you go all the way to resource planning out for decades. And then in the middle you have like hours and minutes and days and so forth, where you make scheduling decisions and unit commitment decisions, and you're trying to see, do your resources fit your demand? So, and then you can do another graph like that in space, and you can go from, meters, which is relevant for power quality, to kilometers at the distribution scale to hundreds of kilometers at the transmission scale. And my personal definition of a smart grid is one that allows you to observe and control quantities on the far ends of these spectra. That is mostly focusing on the very fast end of the time spectrum, and also zooming in on the more local kinds of controls, but while remaining cognizant of what's happening at the other end. So you're not just focusing on the here and now in the absence of any awareness of what's the strategic direction you're going in. It's basically expanding the range of what you can observe and control. And that, to me, at the most generic level, is smart grid. And then you can use it for a whole lot of different things, whether it's a physical analysis of power flows, which is what I personally am working with, or whether it goes into the economics, as in one of our projects, and you'll hear more about that after lunch. So I don't know if that answers your question.
I'd like to add a little bit on that. So
I just want to give my take on definition of smart grid. So a dumb grid, or traditional grid, has the source of generation responding to the load. There's an overload condition, frequency drops, all your generators will pick back up and respond and output more power. Whereas in contrast, a smart grid is the case where the load responds to the generation, so to speak. So if there's an overload condition, then maybe some things on the load side will respond to that, demand response, so to speak. So that's my kind of high-level, very vague definition of smart grid versus a traditional grid. The load responds to the source of generation.